Okay, this is the last section for Chapter 8. The first 3 sections are what you actually need for working the lab that I just posted for you, lab number 2. And with the extra here of section 8.4, you will be ready for your quiz that is scheduled to be due on the 14th of April. In this section, it allows us to figure out ways to calculate the area of a triangle. When we were little, this was one of the things that we automatically learned how to do. And we were always told that the area of a triangle is going to be A equals 1/2 base times height. What a lot of us didn't really think too much about at that time was the fact that we have to know what the height of that triangle is, and the height and the base always must be perpendicular to each other. So if that's the base, and inside here happens to be the height that's going straight up and down, then we could automatically use this formula. Well, because the letter A here in when we work with triangles, sometimes we'll refer to a vertex instead of A is area. We're going to change the letter from A to K. Okay, so we're going to say the area K. So if you end up in a situation where you know the base and the height are definitely perpendicular to each other, you can slip into this formula from our past. That H that we're looking at there is what we normally would see. It's also called the altitude of the triangle. And you can actually have altitude, an altitude drawn from every one of these vertices. So every triangle actually has 3 altitudes. When we start looking at some of the triangles, though, we're going to find out that we do not have where the base and the height are known, much less are they perpendicular to each other. And so one of the situations that we're going to be under is what happens if someone gives us a side angle side type triangle. But this time we want to calculate its area. We don't really care too much about what the actual missing information is. We just want to know what the area of the triangle is. So if you'll go with me here through this, let's see if I can get a pen color here you can read. And it says that in general, the theorem above can be used if H can be related to 2 sides and an angle. Using the rules for right triangles, the measure of angle C. So if we look right here at angle C, and we're focusing in right here the fact that angle C is part of a right triangle, right there, okay. Then we can actually calculate the value of angle C by looking at the height and the hypotenuse of that right triangle. We can't use the adjacent because this value of B down here actually goes from vertex to vertex. So I don't know really any information about B that'll help me with this smaller part of the right triangle. So what it says is that the measure of angle C is related to side H and side A, which is the hypotenuse of the right triangle, by the sine function. And if you think about what sine was telling us, sine says if you know something about your opposite and you know something about your hypotenuse, that's the SOH part of the SOHCAHTOA. So you and I would have the sine of opposite, which is H, over A. If we solve this little equation here for H, you end up with multiplying both sides by A. So H we find out, which is the height, is actually A times the sine of angle C. If we substitute that into our known formula, the area of a triangle is 1/2 BH. If we substitute in the value for H here that we got, and now just kind of go through alphabetizing the variables. A times B is what we would write, then times the sine of angle C. So what we've just found is one of the three forms of the finding the area of a triangle if it's an SAS model. So if you look back down here at the bottom, it will tell us a little bit about the different formulas that we end up with. It says the area K of the triangle equals 1/2 the product of the length of two sides and the sine of their included angle. Once again, all three of these forms really come from the same exact form. It's just the fact that if you and I are looking for, if you and I are given something about angle C and we know something about side A and B, then we can calculate the angle of the triangle's area. If we know something about angle A and we know about side B and C, then we can also calculate that same area. And likewise, if angle B is known. So with these three versions of the same formula here, it just kind of depends upon what angle's given and did you get the two sides that are on either side of it. So let's look at a problem here. And it says find the area of an SAS triangle. And we know that B is going to be measured to be 8, C is measured to be 5, and A is measured to be 40 degrees. Once again, a lot of people will catch on to this formula pretty nicely. I'm asking you to just bear with me here, and I'd like to draw out a basic triangle of what we know. I'm going to let this be angle A. I know that it's a 40-degree angle according to the given. I have side B. I could call this side B right here, that's 8. I could call this here C, which is 5. And when I go in to close up this triangle, then the information that I don't have, again, this is not asking us to solve for all the different parts, but it's good practice to go ahead and make sure you know where all the parts would be. Okay. So it's obviously an SAS model. And so now we can look to see what we've got. We've got angle A and sides B and C. So to calculate the area of this triangle, it's pretty straightforward. K is equal to 1/2. The two sides we have are 8 and 5. And we're going to use the sine, remember, to get the height that was the sine of. And so we're going to the sine of 40 degrees. If you'll go into your calculator and then check out what this value will be. We are looking for area here. In this instruction, it said, please round to 2 decimal places. And so we'll find that our K value is 12.8. Looks like it'll be 12.86. Now, they also said make sure that after you round your answer, make sure you label it correctly. And what they mean by that is, I'm not sure if this was feet or inches or whatever the case is. So we're just going to write the word unit and put a little squared up here, because this lets me know that you understand you just calculated the area. You just now for me found the area that's inside of this triangle. That's what you just calculated. So that's why we have a squared unit. Okay. If we go to this next example here, you'll notice that this time that they are giving us what they call a side, side, side. So when you're given 3 sides of a triangle and you're asked to calculate its area, we use something called Heron's formula. This is a formula that they've traced back to Greece and back in the time of Aristotle. And this was something that actually survived the war. and found it on some tablets or papyrus paper, and we now have it also. Its use is that if you know the three sides of the triangle, you can actually calculate its area. They do require you to perform one thing, and that's to find the semi-perimeter. And so let's look at the semi-perimeter first of all. The definition of perimeter is add up all the sides of the triangle. Semi-perimeter means take half of that. So we're still going to go in there and add the sides together, sides A, B, and C, but we're going to take half of it. The letter that they use for semi-perimeter is the letter S. And because my S's look a lot like 5s, I'm going to use a cursive S instead. So Heron's formula says this: if you know all three sides, you can calculate the area by taking the big square root here of S times S minus one of your sides A times S minus another one of your sides B times S minus the third side C. So we'll have to do some adjustments so that S minus A, S minus B, and S minus C are taken care of, and then we'll multiply it one more time by the semi-perimeter and take the root of that product. This one is, like I said, very plug and chug. You'll notice in the given here, there's no angle. So we're definitely on an SSS triangle. So when you have an SSS triangle, you're going to go straight to Heron's formula. And start plugging in the information you know. The first thing that you want to do, though, is to go ahead and find your semi-perimeter. And we need to know what is the half of 9 plus 6 plus 4. And if you calculate this value here, what's that going to give us? 19 over 2. So how about 9.5? If that's our value for S, then the second thing that we'll do is we're ready to go calculate the area. We'll have 9.5 times 9.5 minus 9 times 9.5 minus 6 times 9.5 minus 4. And now if you'll go to your calculator and calculate the area of this triangle, and you'll get some value of 9.56 to 2 decimal places. Once again, they didn't tell us what unit we're in, so unit squared. And that's how you calculate the area of an SSS triangle. So we have some applications then. Both of these are relatively straightforward for you. This first one here says that the painter needs to cover a triangular region with sides of 24 feet and 18 feet. The angle between these two sides is 100 degrees. And find the area of the region to the nearest, this time, 10th of a square foot. This time we have our unit. So again, probably what I would do is, I know I have a side of 24 feet. I can mark that. I have an angle of 100, which is a little bit bigger than the 90 degrees, so I know that's going to be 100 degrees. And my other side is 18 feet. And so the other side of the triangle must be there. So it's just a way to make sure that you know that you have an SAS triangle. And if we have an SAS triangle, then we can go straight to K is equal to 1/2. One of the sides times the other side times the sine of 100 degrees. And calculate this in your calculator. And it gives you a value of 212.72 if you round that. This is in feet squared. Okay, you're painting the interior of that triangle. So 212.72 feet squared. In the last example here, number 4, we've got another painter. He wants to also cover a triangular region. Notice the given. He's measured all 3 sides. So we're finding the area of the triangle where all 3 sides are given to us. So what this tells me right here then is I've got side, side, side triangle, which means go straight to Heron's formula then. This one has a second part to it. It says, if each can of paint can cover 175 square feet, then how many cans of paint are needed? So he doesn't really want to know what the area is. He just wants to know how many cans of paint do I need. So the first thing we'll have to do, of course, is since we have a side, side, side triangle, I've got a 40-foot, 50-foot, 46-foot triangle. And so I definitely want to use Heron's formula, but I have to figure out what the semi-perimeter is first. So if you'll take half of the sum of the sides, then that will give us 68. Heron's formula said that you can take the semi-perimeter, multiply it by the semi-perimeter minus one of the sides, times the semi-perimeter minus the second side, times the semi-perimeter minus the third side. So if you put that in your calculator then, go straight for the square root. We have 68. And then 68 minus 40, and then 68 minus 50, and 68 minus 46. Let me double check my work. And you should have gotten something like an 868.32. This is, you can also write square feet as SQFT. That's another way to write it. Again, like we said, this is not what they want to know from us. They want to know how many cans of spray paint do we need. And so if we take what 1 can will actually cover and divide that into 868.32, let's see how many cans we will get. And the number of cans, according to our calculator, is 4.96 blah, blah, blah. Well, no one's going to let you buy 4.96 cans, and so we're going to have to go ahead and round that. And so it looks like we're going to need to buy 5 cans of paint. Now, it's not just because it rounded to 5. Even if, just suppose that you and I had ended up with a 4.12 cans, then you're also going to need to round that up to 5. So anything over the whole number is going to cause you to have to buy another one of whatever, like in our case, another can. So 5 cans of paint will actually cover this area. All right, and that's all there is to it.